working with the chi-square distribution and performing a chi-squared test. Get started. The chi-squared distribution is basically right skewed. You can see that the blue distribution is right skewed, and the red distribution is right skewed, and even the green distribution is right skewed. You can tell that the larger the degrees of freedom is, the less skewed it is, and it actually approaches normality. That's not. We don't have to have a normal distribution here, though. So even if degrees of freedom is 1, we can still use a chi-square distribution because we know how probability works for this specific distribution. So we have a chi-squared statistic. And if you notice here, we have observed minus expected. We're trying to basically get the difference of what we actually observed and what we expected to observe. Now, just like with the standard deviation, sometimes that's going to be positive, sometimes that's going to be negative. So we're going to square that to make them all positive, so we can actually get an idea of what that difference is. Okay. So, and notice that that's why this is squared. We have almost like a variance here. We're in squared units. So we're going to take that difference, square it, divide it by the expected. That is the chi-squared distribution. Okay. So we have, first thing we're going to learn about is the goodness of fit test. And the degrees of freedom for a goodness of fit test is n minus 1, where n is the number of levels for the variable. So we'll look at an example. It says a professor concerned about the number of blue M&Ms in his hand decided to collect some data. Here are the observed counts. So this is what we actually observed, the number of M&Ms that we actually observed. And this is what the company is stating that their distribution is. Okay. And we're going to say, is this distribution as the company claims, or is it off? So first of all, we have 6 levels, where one variable is color, and we have 6 levels. So our degrees of freedom is 5. So what we need to be able to do is get an expected value. So first of all, our original hypothesis is that the distribution is what the company claims. We're trying to get some evidence. Our HA is going to be, our alternative hypothesis is going to be that it's actually different than the claim. Okay, so we got to get evidence for that. Remember, we always assume it's innocent until we can prove it's guilty. So that's what we're trying to do here. So we need to get some expected values. Well, if you expect 30% of the M&Ms to be brown, then you expect 30% of your sample size, which we don't know yet, but you just add these numbers up, you get your sample size. We expect 30% of these total M&Ms to be brown, 20% of the total sample size to be yellow, and so forth. So the degrees of freedom is 5, and again, the expected value for brown, you do 30%, and 509 was actually adding up those. That's for our sample size. We sampled 509 M&Ms. We expect 30% of that to be brown. So if I go back, we actually got 152, which is really close to the expected value of 152.7. So if we go to a list here, I'll show you what I've done here. L1 is simply my observed values. 152, 140, that's the observed values for all of these. And L2 is my expected value. So I'd have to do that, 20% of 509, that's 101.8. Again, these are 10%. 10% of 509 is 50.9. So you get your expected values. Now I'll show you what we've done here. L3 is the difference between the observed and the expected. Notice that some of these are negative and some of these are positive. So in this category, it doesn't say it anymore, but in this category, I'll do it again. We took L3, which is the difference, squared it. That's the observed minus the expected squared. And then we divide it by the expected, which is L2. Okay. Now that this is what we call our contributions to our chi-squared value. The larger the contribution, the more that particular color or whatever you're talking about, in this case color, whatever that color had was the most different from what we expected. Notice that we're dividing it by the expected value, so the larger the number it is, that kind of factors that out. So this is actually the biggest, these two are the biggest, or this one's actually has the biggest contribution to the chi-squared value. Okay, so that's an L4. And the chi-squared value says if we sum those up, L4, we get our chi-squared value of 4.09. So that's our test statistic. And we can turn around and get our p-value, which we're going to use chi-squared CDF. We're going to say how rare is that a chi-squared value of that. So our lower bound is what we just found. Remember, this is a right skew distribution always, and a chi-squared distribution, you're always finding the probability of the right tail, either getting a difference that much or more. Because remember, we're always doing the difference between what we expected and what we actually got. So the only evidence against the null hypothesis is if we get bigger differences. So we're going from that to our upper bound. And as we said earlier, our degrees of freedom is 5. And if we get that, we get a p-value of 0.536, which, as we know, that's not a very low p-value. So we did not get any evidence against HO. So we would have to fail to reject HO. We didn't get any evidence that says that it's different than what the company claims. Okay. Now, you can do all this in one step. If I go to stat tests, it's at the very bottom, so I'm going to go up. Chi-squared goodness of fit test. So if I run that, I already have my observed in L1, my expected in L2. My degrees of freedom is 5. And we get my chi-squared value, we get our p-value, and we get our contributions, which was what our L4 was. There's a built-in list called CNTRB, stands for contributions, and that's just the contribution of each one. So if you wanted to see which color had the biggest impact on our chi-squared value, you would look at see which one the largest one was. Okay, so that's how to run a chi-squared goodness of fit test, and again, we would fail to reject because we have a high p-value. The other type of chi-square test we're going to do is basically two different tests, but they're run the exact same way, and I'll talk about what the difference is. The chi-square test of homogeneity and the chi-square test of independence. So, and again, I'm going to show an example, but to get the expected value for a cell, you're going to take the total, the row total, times that column total, and then we're going to divide it by the total, the table total, the total sample size. Okay, and the degrees of freedom here are rows minus 1 times columns minus 1. So we'll look at an example. It says, do Republicans, Democrats, and Independents differ about do they think differently about the primary system in the U.S.? Each group was asked if all primaries should be held in June of presidential election years. 718 Republicans were asked, 734 Democrats were asked, and 76 independents were asked. The results are shown below. So we're trying to get, is there evidence that these groups think differently on this issue? So we're trying to get evidence for that. That's our HA. Our alternative hypothesis is that they're different. So that makes our null hypothesis, remember we're assumed innocent until we are proven guilty. Our null hypothesis is that they don't think differently. They think alike. There's no difference in this group versus that group versus that group. Okay. So here are our totals. We have our row totals. Add up these three values, you get 718. Add up these three values, you get 734, so forth. These are our column totals. And this is our table total, or our total sample size. We sampled 1528, or 1,528 people. Okay. So the degrees of freedom, we have 3 rows, so 3 minus 1, and 3 columns, 3 minus 1. So we get 2 times 2. Our degrees of freedom is 4. And the expected value, you'd have to do this 9 times. But your expected value would be for Republicans who thought it was a good idea. So we're talking about this cell right here. Republicans, good idea. The observed value is 266. The expected value, we take the row total, 718, multiply it by the column total, 602, and divide it by the table total of 1528, and we get this. So that's our expected value. And we need to do that 9 times to come up with our expected value. So, and one thing here, so the chi-squared value, we're going to have 9 contributions. What we're going to do each time is we're going to take the observed 266, subtract the expected 282.877. We're going to square that difference, and then we're going to divide it by the expected again, which is 282.877. Okay, that's how we're going to get each contribution. Then we add up those 9 contributions. That will give us our chi-squared value. So now we're going to go into second X inverse right here, which is the matrix category. And you can see here that in matrix A, I've put in the observed values. And in matrix B, I've put in the expected values. Okay, and they're rounded to 2 decimal places here. Notice 282.877 becomes 282.88. But I think that the calculator leaves some accuracy, it's just not showing it there. So now, if I go to stat test, go down to the bottom. Now, I don't want chi-squared goodness of fit, I just want chi-squared. Notice that this is true for the independence or test of homogeneity. Everything that we've talked about for this example is the same for both tests. I'll talk about what the difference is in a minute. So my observed is in matrix A. My expected is in matrix B. I calculate it. We get a degrees of freedom of 4. We got that chi-squared value, and we got this p-value. So again, a higher p-value. we do not reject HO, which means that we don't get any evidence that the 3 groups think differently. Okay, we don't get any evidence that the 2 groups or the 3 groups think differently. So the last thing we'll talk about is the distinction between test of homogeneity and independence. Because everything, the way that the problems work is exactly the same. And where it comes from is in how we sample our people or subjects. In this case, it says we have 718 Republicans were asked. 734 Democrats were asked, and 76 independents were asked. So that sounds like we're taking 718 people from the Republicans group. So we're sampling from the groups independently first. Okay, so if that's the case, if you're sampling from each one of these 3 groups, then you're looking at a test of homogeneity. Okay. However, if you look at, let's see, we have 1,528 subjects, or participants. So if the problem said something like we took a random sample of 1,528 participants, and we looked for we asked them basically 2 questions: are you Republican, Democrat, Independent? And the other question is, how do you feel about this issue? Okay, so one group, we asked them 2 questions. That's test of independence. So before, if you took a group of Republicans and you're really just asking them 1 question: do you think it's a good idea, poor idea, or no opinion? Okay, so that's the difference between test of homogeneity and independence.